Alright, so this video is going to be covering section 1.1 in the Discrete Math book by Susanna Epp, which is about variables. There's a point I want to make that I don't think is made very strongly in the book, which is sometimes people feel like variables are just another way of saying fill in the blanks. Right? I might say blank is even, maybe I'll put another word up here. If blank is even, then blank squared is even. And I'm intending to say, the idea that if you've got some number that's even, then if you square that number, you'll also get an even number, which I hope makes sense. But the problem is that if I have blanks there, I feel like you can fill anything into them. I could say if 8 is even, then pick something else for this blank, like 7. Right? So it says if 8 is even, then 7 squared is even, and that's crap. That's nonsense. What variables do is get away from this ambiguity that you have when you have blanks or little boxes that you're going to fill in or whatever. It says, yeah, this is a blank, but this blank has to be equal to that blank. That's one of the major features of using a variable. Let's change this whole thing so that it says if x is even, then x squared, sorry about the ugliness there, x squared is even. Now I know that blank and this blank, even though, x is still just a placeholder, a thing that gives us a position to fill in later. But they're the same thing in those two spots. X being even implies x squared is even. The book makes two comments about the utility and the reasons why one might use a variable in a sentence. And the first comment I would call utility. If you write a sentence with an x in it, you can often use that to go back and figure out what x is. So when I say utility, I mean it allows you to determine the actual value or values for the variable. I'm not sure this is the way I would say it, but this is the way I hear students say it. It allows you to find the values that work in the sentence. So suppose I had a sentence. The double of a number. I'm going to try to write this out in words, so excuse me, it may take a little while. The double of a number is 3 more than 2 plus that number. When you write math out in words, it's often really hard to follow. It's kind of interesting that back in the day, like in Euclid or ancient Greece, this is how they had to write math. They would say things like these sentences that talked about doing the operations, and they didn't have x yet. And this utility I'm about is really the value of getting an x. So when I say the double of a number is 3 more than 2 plus the number, I think I'm writing this, that 2x is equal to 3 plus 2 plus x. That's a lame sentence. I don't know why I did that way. Why don't I just say the double of a number is 5 more than the number? That would have been so much cooler. Let me fix this then. And you see what the issue is, that when you're writing stuff out in words, it just does, you lose clarity. But as soon as you see 3 plus 2 plus x, you're like, why didn't they combine those? The double of a number is 5 more than, whoops, I want to leave the word the there. 5 more than the number. Okay, now we've got a sentence, and here's a translation of it into a mathematical expression with x in it. And actually, it's not a challenge to figure out what x is now, is it? You take x away from both sides and you end up with x equals 5. So that's utility, right? Once you've written down a mathematical sentence with x in it, you can turn that into an equation and solve it. And so you figure out what x value actually satisfies your sentence. That's one reason for using a variable in a sentence. The other one, let's just, oh, the whole thing, I guess. The other reason you sometimes want to use variables is generality. Which means you're saying something that you think is sort of always true. So you don't want to say it about 3 or about 7 or about 19. You want to say it about any number, x. Right? So, well, that first sentence I wrote down works this way. If x is even, then x squared is even. Just going to squeeze that into the end there. So that's something that's sort of true no matter what x is. Right. Actually, that gives us a great example of one of the categories of sentences that have variables in them we're going to look at. They're known as universal sentences. Or just universals. A universal sentence is one that is true all the time. If x is even, then x squared is even. That's true for all numbers x. So this is in the category of things that are always true. I got to make a pedantic point here. It's just, it's bugging me. It's not always true, like for anything that you might stick in for x. It's true for certain things. The things that it's true for are numbers. If I said, you know, x is a real number, and then if it's an even real number, which means it's actually less than a real number, it's an integer, but anyway, if it's even, then its square will be even. So it's always true, but the universals, when you write universals down, it always actually depends on what universe you're thinking about, right? So, yeah, I won't belabor that too much, but do realize there's always a context for your math sentences, and we'll be looking at this in chapter 3 in greater detail. So universal sentences are always true. What I've got up here is a universal sentence. There's usually no words that clue you into that, but if you're being kind to your reader, you put them in. So if I wanted to make this a kinder sentence that was a general thing that was always true, I'd say something up front like, for every x, comma, if x is even, then x squared is even. But it tends to be the case that a lot of times people just write down universals, and the act of saying, hey, I've written it down, means I think it's true all the time. So watch out for that. But there's other words that you may run into. So I just gave you one. There's for all, for every, a little bit too wordy, I think, but here's one. It is always the case that. I just said it differently than I wrote it, so you sort of got 2 for 1. It's always the case that, or it's always true that. Those are sort of synonymous. In fact, all of these are synonyms. They're just English phrases that let you know, hey, this thing is a always true sentence, not a sometimes true sentence. In fact, I just accidentally used the distinctions that people normally make about universals versus the other kinds of sentences. We talk about always true, sometimes true, and then never true. Those are sort of three gradated possibilities for a sentence, right? It's either always good, well, once in a while it works, but it doesn't always work, and it's nonsense, it never holds. In fact, when you studied algebra, you ran into algebraic equations that were, that had these sort of properties. Some were always true, some were never true, and some were true occasionally, but not always. The algebraic versions of these things I've been discussing are known as identities. Let's just number them, I guess. Identities are sentences in algebra that are expected to work for every x value. So that's the always true type. There's a name for the kind of equations that you can solve, that you can find x by doing it. They're called conditionals. And that's the sort of things that are sometimes true. Some x values make them true, and other x values will make them false. So let me just say sometimes, because I think I'm going to run out of room for the word true there. But fill in sometimes true on the end of that sentence mentally. And then there's other sentences or other algebraic expressions that you can write down. They're just nonsense. There's no x that's going to make them work. They're called contradictions. Just to make it clear that, make sure that everybody's on board with this, I'm going to give you an example of each kind of thing. So the things that we think of as the laws of algebra, the rules that we follow when we're doing algebra, those are identities. Like if I had 2 times x plus 1 is equal to 2x plus 2. What I did here was distribute the 2 across that sum and got that, but this is a step that's valid no matter what x is. So I've got an expression that's always true. That's an identity. What if I wanted to give you something that's a conditional? Well, you might have something like 3x plus 1 is equal to 2x plus 5. Could you solve that? Could you figure out what x is? I think I can do it almost in my head. Take away 2x and you'll get just an x on this side. And take away 1 from both sides and you'll get a 4 on that side. So x is 4 works. Which is easy to check back. 3 times 4 plus 1 is 13. 2 times 4 is 8 plus 5 is 13 again. Okay? So that's a conditional. We don't really need to solve it. We just needed to know that it could be solved or that some x values make it true. It's not the case, I don't want to give you the impression that conditionals always have just one x value that make it true. Just that it's not always true. So like for instance, if this was a less than in here, there'd be infinitely many values that make it true. And then there'd be other infinitely many values that make it false. So it would be conditional, but not just a unique answer. Kind of wish I could line this up, but let's just work on the side here and get the last kind. How about x plus 1 is equal to x plus 2. That ever going to work? Right? I mean, if the number 1 bigger than some x is never going to be equal to the number that's 2 bigger. That's a contradiction. Never true. Now, when we start talking about logic, we're going to have names for the first 2 kinds of things, always true sentences and sometimes true sentences. We don't actually need a separate name for the last kind, contradictions that are never true, because what you actually do is if something's never true, then its negation, the opposite of it, is always true. So these things are actually sort of both universal sentences. One's a universal sentence that's actually true, and the other's a universal sentence that's well, false all the time. That's a bad way to say it. Its negation would be true all the time, which is more what we're after. This word right here, conditionals, when you're not in algebra, has a different meaning. We talk about if-then sentences as being conditional, so just watch out for that. A distinct usage of the word conditional is sentences that start with an if and end with a clause that's got a then in front of it. Yeah, so let's say this. If some sentence, then some other sentence, that's a conditional too. I mean, it's in this case, what they're getting at is, by the choice of the word, is the truth of this sentence is conditional on what you put in the blanks. And I do mean these blanks to be different things, okay? So, like, if x is a whole number, just using that sign for the whole number, for the word number. If x is a whole number, then 2x plus 1 is a whole number. I'll extend my blank a little bit. So it depends, right? For some values of x, this thing will be true. But if I got one like I've got right now, which happens to actually be universally true, right? If I have something that's got nothing after the decimal point, if I do these operations, double it and add 1, I'm going to have something with nothing after the decimal point again. So this is universally true. And that makes what we just did right there a conditional sentence that's also universal. And there's a special name for that, a UCS. That means a universal conditional sentence. Right now, we're not going to do too much with UCSs. I just sort of want you to know that they exist and that they're important, and we'll start a little bit on how to handle ourselves relative to UCSs, translating things that are given in sort of natural language into them. One way to think about these conditional sentences is a sort of forcing idea. When you say if then something, if something then something else, the something being true forces the something else to be true. So if you've got an x that actually is a whole number, that is going to force that its double plus 1 is a whole number. So that's one way to think about it, is forcing. I want to point out, particularly to people who have programming experience, this is not how we think about if-thens when we're writing code. Let's see. Let me write it this way. If we have if A, then B. If you're writing code, you say something like, if A is true, then do this. It's not saying this is true, but rather this is what's going to get executed next. That is different from how they think about it in the math world or in the logic world. It's just that this thing being true will force that this thing is true. I suppose we normally don't think in computer science of the other thing as being a statement even. It's just a collection of actions that the code is going to execute once it knows that A is true. A block of code, right? So that's a distinction to make. Don't think about computer science if-thens when you're doing logic if-thens. Okay, and that really brings us to the end of section 1.1. There's one more video in this sequence about 1.2. I will try to get it out as soon as possible.